Tonight, I'm delighted to bring up our introducer for the evening, Brian Hopkins. He's a mathematician at St. Peter's University, and he's also a recent editor of the College Mathematics Journal, and he's been a friend to the museum for a long time. And if you look carefully on our website, you might notice that he'll be back with a wonderful performance of his own in the winter. So for now, I give you Brian Hopkins.
Thanks. So I'm very pleased to be able to introduce to you my friend David Richeson. He is a professor at Dickinson College over in Carlisle, Pennsylvania. Just to give a shout out to some institutions, he went to undergraduate at Hamilton College, upstate, and then Northwestern for his PhD, and did some postdoc work at Michigan State University. I think Dave and I first met about 2007 or so. It was a good year to be a history of math person. It was the 300th anniversary of the birth of Leonard Euler, and there was lots of interest in looking at his mathematics and talking about it. We ended up being in some books together, I think. And Dave took that work and then made a book with Princeton University Press called Euler's Gem, which did very well. It had an interesting subtitle, The Polyhedron Formula and the Birth of Topology. And this is very well received. It went on to get the Euler Book Prize. And that's not because the content was about Euler. Instead, the Euler Book Prize is for, I'll read the citation, it recognizes authors of exceptionally well-written books with a positive impact on the way that the public views mathematics. So he did that, and no good deed goes unpunished. So after writing a good book, he became the editor of one of the Mathematics Association of America's journals called Math Horizons. This one is especially intended for undergraduate students, but of course is open to anyone who likes to read engaging, lively articles about mathematics in kind of a magazine format. I, at the same time, was, as Cindy mentioned, the editor of the College Mathematics Journal, so we shared a lot of time in tedious meetings and council Zoom meetings and all kinds of things talking about publications. But luckily, we also had the chance to interact with some mathematics. Dave wrote an article for the College Math Journal called, on the topic of who first figured out that if you take the circumference of a circle and divide it by the diameter of the circle, you get this constant that we now call pi. Who was the first person who did that? Great article. Ended up going into a collection called The Best Writing in Mathematics for that year. And then he went on after that and has another book. And just in case he's too modest to push it, I brought it up here with me. It'll be over at a table back over there. Actually, the Euler's Gem is there too, and also this Tales of Impossibility, which is the foundation for the talk that you are about to enjoy. So a lot of us here have, in our profession, the joy of trying to elucidate mathematics, to bring this potentially complicated topic to a wider audience and explain why it's engaging and why it's fun. And some of us do that in teaching, some of us do that in writing, some of us do that, as the museum does, with very engaging exhibits. Dave does this in writing and also with attention to the history behind the mathematics, who did things, why they did things, bringing in the human element. So I hope that you'll enjoy Dave as much as it went well in the first talk. And we're lucky that he's here. He left his wife, 2 children, and 43 real analysis students back in Dickinson College to be here with us. So, Dave Richeson.
Thank you, Brian. Thank you, Brian, and thank you, Cindy, for the invitation. It's a pleasure to be here. I've been a fan of the Museum of Math since before it was the Museum of Math. I visited the Math Midway when it was traveling around the country, and I've been back to the museum with my son, who has really enjoyed it. And I come back when I can to the MOVES conference, which happens every other year. Unfortunately, I could not make it this particular year, so it's a real treat to be here to speak to all of you. Before I get started on my talk, everyone should have one of these handouts at the table. We're going to have a few activities, and so while the talk is going on, you can cut out all the tools here. I hopefully punched out the hole in all of the compasses here. We don't have compasses, so I have what I'm calling a rusty compass here, and these are going to help you draw circles at some point during the talk. We have a ambitious agenda for today's talk. We're going to talk about 2,000 years of mathematics. I'm going to talk about these famous geometry problems and the eventual proof that they are impossible. So we've got a lot to say, so why don't we get started? So as we all know, nothing is impossible, right? This is the American dream. Robert Goddard had something to say about this. He wrote, "Just as in the sciences we have learned that we are too ignorant to safely pronounce anything impossible, so for the individual. Since we cannot know anything, we cannot just know what are his limitations, we can hardly say with certainty that anything is necessarily within or beyond his grasp. It is often proved true that the dream of yesterday is the hope of today and the reality of tomorrow." Even Shel Silverstein got in on the conversation. He wrote, "Listen to the mustn'ts, child, listen to the don'ts. Listen to the shouldn'ts, the impossibles, the won'ts. Listen to the never haves, then listen close to me. Anything can happen, child, anything can be." Right? This is what we tell our kids. This is what athletic coaches say. This is what teachers tell their kids. And I'm sorry to be the bearer of bad news that this is not true, that there are things that are impossible, and we can use mathematics to prove that they are impossible. So just as one example, you guys may know this puzzle, which you can get at Cracker Barrel gift shops or wherever. It's the 15 puzzle where you have to slide the tiles around and get them in numerical order. Well, there's a famous example from the late 19th century. The puzzler Sam Lloyd had one of these 15 puzzles, but he deviously switched the 14 and the 15 in the puzzle, and he gave a monetary prize. He offered a monetary prize for anyone who could solve his particular puzzle. But little did his customers know this is impossible, and you can use mathematics to prove that if you make that simple move of switching the 14 and the 15, then this becomes impossible to solve. And so he never had to pay out the prize money. So that's one example of a mathematical impossibility. There are many others, so just a few examples. Famously, Leonhard Euler analyzed these 7 bridges that crossed the River Pregel in Königsberg, and the people from that city wondered whether you could find a walking route that would cross every bridge one and only one time. And it turns out that that is impossible, and Leonhard Euler proved it. I also want to give a plug to Brian, who introduced me. He co-authored a lovely article about the bridges of Königsberg, which I would highly recommend. Another famous impossibility problem is Fermat's last theorem, which was proved in the mid-90s. And this is sort of a generalization of the famous Pythagorean identity. But in this case, we're looking at exponents n that are 3 or larger. And we want to know whether there are integers that satisfy this relation. And famously, you cannot. So there are no solutions to this when n is greater than or equal to 3. Another famous impossibility problem, we often ask our algebra students to solve polynomials, look for roots of polynomials. And linear polynomials are easy. If we have a quadratic polynomial, a degree 2 polynomial, there's the famous quadratic formula that helps you solve those. It's a much messier procedure, but you can solve degree 3, you can solve degree 4, but famously, it is impossible to have a general formula for degree 5 or higher. So that's a famous impossibility problem. We all just voted, hopefully we all just voted yesterday. There's a famous impossibility theorem in voting theory. So Kenneth Arrow listed a bunch of very reasonable traits that you would like a voting system to have. And he proved that it was impossible to find a voting system that satisfies all these reasonable criteria. And probably the most meta of all of these impossibility problems is something called Gödel's incompleteness theorem. And this lives in the realm between logic and mathematics. And Gödel proved that if you have any sufficiently sophisticated axiomatic system, that there are true theorems, true statements that cannot be proven. So this is a very interesting impossibility theorem. So these are just some examples of impossibility theorems in mathematics, but there are 4 of them that I want to look very closely at today and to talk about their history. So we will see that it is impossible using only a compass and straightedge to double the cube, to trisect every angle, to construct every regular polygon, and to square the circle. And so the structure of my talk is we're going to spend quite a bit of time talking about each of these four just to make sure we understand what the problems are. Then we're going to talk about a period where people tried to solve them using various means. And then at the end, we're going to talk about the eventual proofs that they are impossible. And just so that we're sure we're on the same page, what these things constitute, we can transport ourselves back. In my case, it was 10th grade, where in the geometry class, the only tools we have at our disposal are a compass and a straightedge, and you want to solve some certain geometric problem. So in this case, let's say we have a line segment, and you're asked to draw the perpendicular bisector for this line segment. So I will show you the procedure, which you may remember from high school. So you can draw a circle with the radius equal to this line segment, another one with the center at the other end. That gives you these two bullseyes, and you draw a line segment between them, and this is the perpendicular bisector of the line segment that you started with. And so this is a straightforward procedure and something that a typical 10th grader would learn in a geometry class. And so these four problems are in some ways just as elementary to state as this problem from 10th grade. But these happen to be impossible to solve. So let's look at them one at a time. I'm going to start with what looks at a glance to be the weirdest one. So this has to do with cubes, but we're really talking about planar geometry. But this really is a question in planar geometry. The question is, if we start with just this line segment, the side of a cube, is it possible to construct the side of another cube that has twice the volume? Okay, so what I'm going to do for each of these problems is I'll tell you what the problem is, then I'll show you an easier version of it, and then we can return to the difficult one again, the impossible one. So let's drop down a dimension, and let's talk about doubling a square. So suppose you have the side length of a square. Is it possible to construct the side length of a square that has twice the area? So let's just say our original square had side length 1. So the area of the square is 1. We would like to construct the side length of a square with twice the area, area 2. Okay? So if this has side length 1, has area 1, this has area 2, so the side length is square root of 2, right? So really, this is going to boil down to a question about line segments. So if you start off with a line segment of length 1, is it possible to construct a line segment of length square root of 2 using only a compass and straightedge? And so it turns out all of our problems are going to boil down to something like this, a question about constructing line segments of various lengths. So here's our square with side length 1. Is it easy or hard to construct a line segment of length square root of 2 from this? Easy, right? That's it, right? That has length square root of 2. And so this square is going to have twice the area of this square, right? So this seemingly similar problem is almost trivial. Okay, so let's go back to our cube here. Let's say that our original cube has side length 1. So you start off with a line segment this long. We want a cube, the side length of a cube of volume 2. And so now, instead of square root of 2, our side length is going to be the cube root of 2. And so just like for doubling the square, it boils down to line segments. If you start off with a line segment of length 1, is it possible, using only a compass and straightedge, to construct a line segment of length cube root of 2? Okay? So if you can do that, you can double the cube. Okay. The second one is the problem of trisecting an angle. So I want to clarify one thing about this problem. The question is, can you take an angle and divide it into 3 equal angles? And here, there are some angles where you can do this. But the question is sort of a generic question. If someone handed you a random angle, an arbitrary angle, are you guaranteed to have a procedure for dividing it into 3 equal subangles? Okay? So again, let's look at an easier version of this. If you're given an arbitrary angle, can you bisect the angle? And so just like our perpendicular bisector problem at the beginning, this is a typical high school geometry problem. So you might even remember how this goes. If we draw a circle with a center at the vertex, and then you draw 2 circles with this radius, then that will give you this bullseye, and you draw the ray, and that splits our angle into 2 equal subangles. So very easy to solve. our impossible problem is splitting it into 3 equal subangles. So for this discussion, let's work things in reverse. Let's assume that we can trisect the angle. So we can draw this ray where this angle has size theta over 3. Then we can draw a circle, any circle that has a center here. Let's just say it has radius 1. We can drop a perpendicular down from this point. The distance from the center of the circle to the foot of this triangle, if you do a little trig, that's cosine of theta over 3. So if you can trisect the angle, then you can construct this line segment of length cosine theta over 3. But actually, all of those steps are reversible. So if you can construct this line segment of length cosine theta over 3, you can draw this perpendicular, and that gives you this point, and we can trisect the angle. And so just like our previous problem had a number associated with it, so does this one. So if you start off with a line segment of length 1, is it possible to construct a line segment of length cosine theta over 3 for any theta that you're given, right? So for a generic theta. And if so, you can trisect an angle of size theta. Okay. The next problem is really a class of problems. We want to know, can you construct every regular polygon with only a compass and straight edge? Okay, so these problems date back to the Greek period. If you look at Euclid's Elements, there's a lot of constructions in there of various regular polygons. In fact, the very first proposition in Euclid's Elements, you construct a regular, an equilateral triangle. Okay, so some of these we can do, but the question is, can we construct all of them? And I should point out here that I'm phrasing this in terms of regular polygons. An equivalent way to think about this is that if you have a circle, can you divide the circumference of the circle into n equal parts? If you can divide it into n equal parts, you could connect the dots, and that gives you your regular polygon. And so sometimes when you see people talking about this problem, they call it the circle division problem, so dividing it into equal parts. So let's look at an easier version of this. I think probably the easiest one is constructing a regular hexagon. So we want to construct a regular hexagon inside of this circle. And this is a particularly nice problem because that hexagon is going to have a very interesting property. The side length of the hexagon is going to be exactly the same length as the radius of the circle. And that makes the problem very easy to solve. So if we put the tip of our compass here on the circle and the pencil at the center of the circle, so we draw a circle of exactly the same size, it's going to cross here and here. And because of these properties of the hexagon, these 3 points are automatically vertices of the hexagon. And so once we have these, we can find the other 3 very easily. We can just draw these line segments, and that is our regular hexagon. So that is very straightforward. And actually, almost for free here, if you have the regular hexagon, you could join every other vertex, and that would give you an equilateral triangle. Right? So that's pretty straightforward. Okay, so back to our chart here. We just saw that you could construct an equilateral triangle. On one of the earlier slides, I implied that we could construct a square, and we can. That's not too hard. The pentagon, we can construct a regular pentagon. It's a little bit difficult, and probably for students who are working through Euclid's Elements, this is one of the stumbling blocks to figure out how to construct the regular pentagon. It turns out that the regular pentagon has a very interesting property. If you were to join these 3 vertices, you get an isosceles triangle. And this isosceles triangle has the property that this angle is, or I guess this angle is twice this angle. This angle is twice this angle. And that's sort of the key ingredient you need to construct the regular pentagon. So that is possible. We also saw that you could construct the regular hexagon. In fact, once you have a regular n-sided polygon, you can always double the number of sides. So you can imagine having one of these regular polygons inside of a circle. You could draw rays from the center of the circle to 2 adjacent vertices. You could bisect that angle, and that will give you one of the new vertices of the regular n-sided polygon. So from those 4, we could get the regular octagon, the regular 10-sided polygon, 12-gon, 16-gon, and all the doubles of those, right? So these are all possible. There's one other trick that Euclid had here. The number 3 and the number 5 are prime numbers, and so we can take advantage of that to construct one additional regular polygon. So here we've constructed an equilateral triangle and a regular pentagon inside the same circle so that they share a vertex here. And if you look at these two vertices right here, this vertex is 1/3 of the way around the circle from A, and this vertex is 2/5 of the way around the circle from A, and 2/5 minus 1/3 is 1/15. And so this right here is the side of a 15-gon. And so once you have the one side, you can get the rest of them. Okay? And so by the end of the Greek period, this was all they were able to solve. So the green ones they could solve, the yellow ones had question marks in them. So the first one, the smallest one that was unknown, is the regular heptagon, the 7-sided polygon. The nonagon, the 9-sided polygon, was unknown, as are these other ones. So these were unknown. And I guess we need a number associated to this. The analysis is almost the same as it was for the angle trisection problem. So here, if you start off with a line segment of length 1, then you can construct the regular n-sided polygon if and only if you can construct a line segment of length cosine 360 over n. So that's sort of the number associated with the regular n-gon. Okay, and the fourth problem is probably the most famous of all of these problems. This is the problem of squaring the circle. And so here we ask the question, can you take an arbitrary circle and use only a compass and straightedge to construct a square that has the same area? Okay, so I should point out here that when the Greeks thought about squaring a figure, this was sort of equivalent to computing the area of the figure. If you could draw a square that has the same area as a figure, that means you've sort of captured all of the area. And so the Greeks tried to square all manner of different figures, and the circle, one of the simplest geometric shapes, was outside of their grasp. That was something they could not do. So let's start with an easier version of this. This isn't all that much easier, but it is a little bit easier. Let's try to square the triangle. So let's say you're given an arbitrary triangle. We know you can compute the area. It's 1/2 base times height. And so you could give the geometric version of that by dropping a perpendicular, bisecting that perpendicular, drawing this parallel line, and drawing these perpendiculars to get this rectangle. And if you think about it, this rectangle has the same base as the original triangle, and it has half the height of the original triangle. So they both have 1/2 base times height of the triangle. Okay, so turning your triangle into a rectangle is pretty straightforward. You might think it's trivial to turn the rectangle into a square, but it turns out that's a little bit tricky. So I will show you the steps here sort of one at a time, sort of quickly one at a time. So we can extend this line segment. We can draw this circular arc. Now we want to bisect this line segment, draw this circle. If we extend this line segment up, it hits the circle here. And it turns out that this square, if you follow all those steps, this square has the same area as this rectangle, which has the same area as this triangle. And so this gives us a means to square an arbitrary triangle. And so it turns out you can square any polygon. Euclid could square any polygon. Shapes with curved boundaries were a little bit trickier. There are some examples from the Greek period where they could square shapes that had curved boundaries. So one famous example is that Archimedes took a parabola, and if you sliced the parabola in any way with a straight line, he found a way to square that little sort of fingernail wedge shape from the parabola. But these were difficult problems, trying to square various shapes. And shockingly, the most simple geometric shape, the circle, turned out to be the one that they really wanted to do and were unable to do. So let's take our circle. Let's assume it has radius 1. So the area of the circle is pi r squared. So in this case, pi, because we're talking about radius 1. So the circle has area A. And so we want the square to have area A. And so the side length of our square is going to be the square root of pi. Okay? So just like the other problems, this boils down to a specific number. Given a line segment of length 1, can we construct a line segment of length square root of pi? Okay? Square root of pi is a little bit messy. It turns out if you can construct a line segment of length square root of pi, you can construct a line segment of length pi and vice versa. So we're just going to have pi be a stand-in for square root of pi. Or actually, I took this picture a few hours ago, pi, from the doors of Museum of Math. OK? OK, so just to recap all these slides, in each case, we're going to start off with a line segment of length 1. And if we can construct a line segment of length cube root of 2, then we can double the cube. If we can construct a line segment of length cosine theta over 3, then we can trisect the angle theta. If we can construct a line segment of length cosine 360 over n, then we can construct a regular n-sided polygon. And if we can construct a line segment of length pi, then we can square the circle. Okay? So these are the numbers that are going to be important to us. I'm going to show you this slide again near the end of the talk when we're talking about the impossibility of these problems. Okay? So some of you might be asking, why compass and straightedge? Why is that? Why are those the rules of the game here? And so one answer is that if you think about the most elementary geometry that you can do with as few tools as possible, let's just say a piece of string or something, string with sticks at the end. You could plant this stick in the sand, and you could use the other end to trace out a circle. Or you could stretch your string straight, and that gives you a line segment. So in some sense, these are the most elementary geometric tools that you could imagine. Another answer to this question, though, is that solving these problems really have two parts. One is, here are the steps that you need to go through to solve the problem. But also, you need to prove that your steps actually do what you claim that they do. Right? So you need sort of mathematical theory to back these things up. And the Bible for geometry from 300 BC until the present, more or less, is Euclid's Elements. Okay? And Euclid famously started his book with 5 postulates. And the first of the postulates is that you must be able to draw a straight line from any point to any point. So you can draw a line segment using a straightedge. Second is that you can produce a finite straight line continuously into a straight line. So you can extend your line segment into a line. Third is that you can describe a circle with any center and any radius. And so this basically says you can use a compass. So in order to prove these problems have been solved, you use Euclid's postulates, and 1, 2, and 3 are the compass and straightedge postulates. And so that's another reason why these problems were important. I left some space here for 4 and 5. 4 looks weird to us today. It says that all right angles are equal to one another. And you can see I left a lot of room here for 5. I'm not even going to read this. This is the famous parallel postulate, which itself has a long and very interesting history and could be the subject of a fascinating hour-long talk in and of itself. OK, so now let's talk about solutions to these problems. And I put solutions with an asterisk because they're not really solutions. These problems are impossible. But for many years, people would ask, what if I had a compass and a straightedge and something else? So can I solve these problems if I add some new thing to my bag of tricks? So let's talk about some of these. So one of the things you might add is some new drawing device. So these are all actual things that you might encounter. We have the carpenter's square over here. This right here is a tool that draws a curve called a conchoid. So that's a sort of a specialty compass. This is a tool where these triangles slide to the left and the right, and this line here can kind of move up and down. It's sort of hinged right here. And you can use this tool to double the cube. So in this picture, that length is the cube root of 2. This so-called tomahawk, this is one of the things on your sheet there. We'll come back to that a little bit later. You can use this to trisect any angle. There's all these interesting linkages which can do various things like trisect an angle. This tool down here, this was a drawing device that was invented by Descartes. And you can use this to solve some of these problems. And the origami crane here is a stand-in for a fascinating field of math that I know plays a big role here at the Museum of Math, where people try to take origami and look at it sort of at a foundational level. What are the postulates that come out of origami? And if we could have sort of equivalent postulates to Euclid's postulates, you can ask, what can you construct with origami if you have some certain rules of what you can and can't do with origami. And it turns out you can, for instance, trisect any angle using origami. Okay, so let's look at some examples. So this one I thought you could follow along if you want to. So on your sheet here, we have a marked straight edge. So you can use this just like an ordinary straight edge. You can see there is one mark on the side. And so it turns out that Archimedes, the great Archimedes, showed that if you had a marked straight edge and a compass, you can trisect any angle. So for this activity, I want you to use the marked straight edge and the rusty compass number 1. So this is the bigger circle here. I will add as a little parenthetical note here that I'm calling these rusty compasses. There's a whole area of math where people look at what geometry you can do if your compass has rusted in place and can't open or close. So it's set to a fixed radius. And so this disk is acting like your rusty compass. And just in case you're curious, I've done this in advance so that the radius of the rusty compass is exactly the distance from the mark on the straight edge to the end of the straight edge. I will also add that the marked straight edge, some people say it has 1 mark, some people say it has 2 marks. Really, you have the mark on the straight edge, and you know where the end of the straight edge is. So it can measure exactly 1 distance. Okay? And so what you can do is draw any angle you want on your blank piece of paper. So here's my angle. And I will show you Archimedes' procedure for trisecting this angle using a marked straight edge. Okay, so draw any angle. So the first thing I want you to do is to extend one leg of your angle down here, just as far as you want. Doesn't matter how far it is. The next thing I want you to do is to take your rusty compass and to draw a circle that has the center at the vertex of the angle, and you can draw the rusty compass number 1. Yeah, rusty compass number 1, sorry. Rusty compass number 1. So draw along here. I went through the cardstock and punched out the center with a nail. So hopefully you can see that. If you have to clear it out with your pencil, you can. So this is rusty compass number 1, the larger one. And so I'm showing it here as a circle where the radius is the distance between the marks. Okay. So it looks like I'm already using the marked straight edge, and in a sense I am, but so far I'm not doing anything that Euclid could not have done. Right? I'm not doing anything that Euclid could not have done. It's the next step where we really use the rusty compass. Okay? So this step is going to take a little dexterity on your part. Let me show you exactly what's going to happen. You're going to take the mark is going to be at this end. So this is the short distance from the mark to the corner. And what I want you to do is to arrange it so that the straight edge passes through this point of intersection, so that this corner is sitting on the horizontal line, and so that your mark is exactly coinciding with the circle. So we're really lining 3 things up: this point of intersection, the mark and the circle, and the corner on the horizontal line. Okay? And so if we do that, so it's a little tricky. You can see why it's not Euclidean here. We're lining 3 things up. So this is what you cannot do with an ordinary compass and straight edge. Okay? And if you draw that line segment, then this angle is exactly theta over 3. So this angle is exactly 1/3 of theta. And I realized after the fact I should have made a printable protractor on your piece of paper so you could actually measure it. If you have one at home, you can try measuring it. But this angle is theta over 3 if this angle is theta. And if you want to prove it, I won't prove it for you, but you can. If we draw this line segment here from the vertex of the angle to this point where the line crosses the circle, you see that this right here is an isosceles triangle, and this is an isosceles triangle. And if you just sort of chase around these angles, you can see that this angle is 3 times this angle. Okay? So this is Archimedes' method of trisecting an angle with a marked straight edge. It turns out that the marked straight edge lived on for a long time. There were people who were interested in this geometric technique. Viette was very interested in this. You can do all sorts of interesting things with this. It turns out that Crockett Johnson, who you may know as the author of Harold and the Purple Crayon, and he's also he's author of the comic strip Barnaby. He was interested in mathematics, and he found a way to construct a regular heptagon, 7-sided polygon, using a marked straightedge. And so that was in the 1970s, I believe. So this has had a long life, the marked straightedge. Okay, so that is one of our specialty drawing tools. I also want to share with you a construction that uses the tomahawk, but I think I'm going to postpone that until after. That'll be our ending activity after talking about the impossibility of these problems. So we will return to the tomahawk at the end of the presentation. Okay, so adding new tools is one way to solve these problems. Another way to solve these problems is to add new curves. So suppose you have lines and circles, like compass and straight edge, and then fill in the blank with any curve that you know about. So can you solve any of these problems of antiquity if you have one of these specialty curves? Okay, so let me give you an example of how you might use a specialty curve to solve these problems. So this curve is a very old curve. So this is late 5th century BCE. So this is well before Euclid or Archimedes. And this is a curve called the quadratrix. And we can use this to trisect any angle. And so let me show you how this works. It's a little bit confusing how it's drawn, so I'll show you 2 times. So we're going to draw this square here. And what I want you to imagine is that this top of the square is going to fall like the floor of an elevator. And this side of the square is going to tip over like a tree falling over. Okay? And they're both going to happen at the same time, and they're both going to reach the bottom at the same time. And where these 2 line segments cross, that's what's going to trace the quadratrix. So I'll show you twice here. So these things are falling, and that curve is what we call the quadratrix. So we can show that again. So this is falling like an elevator, this is falling like a tree, and that curve is the quadratrix. Okay, so let's see how we would use this curve to trisect this angle. Okay, so the first thing we can do is drop a perpendicular from here over to this side. I wrote A here. What I mean by A is that this distance right here is A. And it's impossible to trisect any angle, but it is not too difficult to trisect a line segment. So we can find the 1/3 point here on this line segment right here. And so we can draw a perpendicular from there over to here. And this gives us this point right here where this horizontal line crosses the quadratrix. And that gives us exactly the point that we need to trisect the angle. And so this might seem weird and confusing, but I claim that the quadratrix was created expressly for this purpose. So if you think about it, think about this line, the floor of the elevator being here. It falls 2/3 of the way down when it gets to here. This is like the tree tipping over. It falls 2/3 of the way down when it gets to here. And so that's exactly what this point of the quadratrix means. And so it exactly trisects this angle. That's why this curve was created. Okay? It turns out the quadratrix can also be used to square the circle. That's a little bit more of an involved discussion. And actually, that's where the name came from. And that was much later. That was after Archimedes. But here's an example of how you can use a new curve to solve one of these classical problems. Okay? Okay, so now we're going to jump ahead. We're going to jump ahead like 2,000 years. And one of the really fascinating things about these problems is they are problems in geometry, but really we need something new to tackle them. We need algebra, and we need a good understanding of numbers. And so the Greeks did not have the tools to prove them, and they did not have the tools to prove that they were impossible. We had to wait for geometry to be invented or discovered. Okay? And this whole episode of geometry coming into being, I found it extremely fascinating to learn about the history of algebra. There was a lot of pushback at the time. Mathematicians thought that geometry was the way that mathematics should be done, and this newfangled algebra was sort of mathematically heretical. They did not like it at all. And to some extent, people still feel that way today. So I found this amazing quote by Michael Atiyah, who just passed away a couple years ago, and he said the following. So this was in 2001, but it really could have been written in the 17th century. So he wrote, "Algebra is to the geometer what you might call the Faustian offer. Algebra is the offer made by the devil to the mathematician. The devil says, 'I will give you this powerful machine. It will answer any question you like. All you need to do is give me your soul. Give up geometry and you will have this marvelous machine.' Of course, we would like to have things both ways. We would probably cheat on the devil, pretend we're selling our soul, and not give it away. Nevertheless, the danger to our soul is there, because when you pass over into algebraic calculation, essentially you stop thinking. You stop thinking geometrically. You stop thinking about the meaning." So there really was a lot. There we go. So this really was the sentiment when algebra was being introduced. And this spring, I gave a talk at an MAA meeting in Tennessee, and Tom Banchoff, who is a retired mathematician, was also giving a talk at that same conference, and he said the following thing. He said, "I have nothing against algebra except when it takes the place of geometry." So I wrote this down and added this slide to my talk, which was later in the afternoon, and I put it up there, and afterwards he's like, "Can you give me a copy of that slide?" So this was this spring. This has nothing to do with my talk, but during his talk, he had this. This is a donut-shaped balloon. So you could blow this up, and it's a donut, which I think is just awesome, and has nothing to do with my talk, but I want one of those. You should sell them in the MoMath gift shop. So this was the introduction of algebra. And one of our heroes of this whole story is Descartes. And so Descartes really was a geometer, but he started the process of using algebra to solve geometry problems. And he had a lot of contributions to mathematics. The way I want to phrase what he did was he showed how to add and subtract line segments, to multiply line segments, to divide line segments, and to take square roots of line segments. And I'll say more about what I mean by that. And if you can do that, then you can do algebra on these geometry problems. So here's an example. Suppose we have these two line segments, and we want to multiply them. So if we multiply these two line segments, what do you think the classical object that you would get if you were to multiply these two line segments? Yeah, an area, a rectangle, right? You would get a rectangle. So that's sort of the obvious thing to do. The problem is, if we multiply two line segments, it would be great to get another line segment and not to get an area. And so Descartes figured out how to do this. And he had an invention that was ingenious. And what he invented was the number 1. So he invented the number 1. So what I mean by that is Descartes took some line segment on his geometrical drawing, and he said, I'm going to call this 1. So for the rest of this problem, this is 1. And it turned out that was the ingredient that he needed to be able to do arithmetic with line segments. Okay, so let's see how that would work. So let's say we want to multiply line segments A and B. So you can draw an angle, any angle, it doesn't matter. We're going to draw here a line segment of length 1, whatever we have chosen to be length 1. We draw a line segment here of length A. We draw a line segment here of length B. Okay, we can connect these two dots. We can draw a line parallel to this line, and let's call this X right here. So what geometric idea pops out at you when you see this picture? Trapezoids, yes. Yes. Similar triangles. Yeah, so yes, trapezoids. But similar triangles is what we need here. So we have similar triangles, and if you look at this the right way, you could say A is to 1 as X is to B. That gives you this relation right here. And therefore, this length X is what we're going to call the product of A and B. And if you imagine making this with one of those online geometry applets, and let's say that this was movable, that you could change the length of 1. As you move this length, you can imagine this point is also going to change. And so the length A and B is going to change. It's not well defined. It's only well defined when you've chosen how long 1 is. And then for the rest of your problem, you have this idea of how long the unit is. Okay? And in case you don't believe me, and hopefully you do believe me, here is the very first paragraph of Descartes' geometry. So the title of this chapter is problems the construction of which require only straight lines and circles. So we're really talking about compass and straight edge problems. That's what Descartes is writing about. And so this is literally the first page of his book. Let me read this to you. It says, any problem in geometry can easily be reduced to such terms that a knowledge of the length of certain straight lines is sufficient for its construction. Just as arithmetic consists of only 4 or 5 operations, namely addition, subtraction, multiplication, division, and the extraction of roots, which may be considered a kind of division, so in geometry, to find required lines, it is merely necessary to add or subtract other lines, or else, taking one line which I shall call unity, so that was his big contribution here, in order to relate it as closely as possible to numbers, and which can in general be chosen arbitrarily, and blah, 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 blah. And then he talks about the procedures for multiplying and dividing and taking square roots and so forth. So this is what Descartes wanted to do. He wanted to take his geometry problem, turn it into an algebra problem, solve the algebra problem, and then go back and show how the geometry problem is solved. Okay? So here's one way to look at what Descartes did. He said that, let's say we start off with a line segment of length 1, and a is some positive number. And let's say that we can write a using just the integers and addition, subtraction, multiplication, division, and square roots. Then by using his techniques, we can construct a line segment of length a. Conversely, if you think about it, if we're using a compass and straight edge, we're only ever intersecting lines and lines, or circles and circles, or lines and circles. And if you try to solve for these points of intersection, at worst, you're going to be solving the quadratic equation. So you're not going to get anything worse than square roots in your final answer. Okay? And so here's a theorem. This is not the way Descartes stated it, but this is the way we are going to. We're going to ask about constructing a line segment of length absolute value of a. And so what he proved, and we're going to call those a's that can be constructed, these line segments, we're going to call those constructible numbers. So a real number a is constructible if and only if it can be formed from the integers using the 4 arithmetic operations and the square root. Okay? So these last few slides are a little abstract. You might have dozed off here. Let's do some concrete examples. And I apologize, these are all going to be at the bottom of the screen. We do have TVs over there if you need to see them. So here's an example of a number. So is this a constructible number? Can we construct a line segment of length 1 plus the square root of 5 over 2? Yes. Is this a famous number? Yes, it's the golden ratio, right? So this is a famous number. Actually, if we went back to our regular pentagon, and if the side length of our pentagon was 1, then the diagonal of our pentagon is the golden ratio here. So this, we know from geometry that this is constructible, but we know from Descartes' work that it is constructible because it only uses integers, the 4 arithmetic operations, and the square root. Okay, so this is a famous number. The next number is also famous. Okay, I'm kidding. That's not a famous number. But is it constructible? Is this number constructible? It is, right? It's written using the integers, square roots, and the arithmetic operations. So this is a constructible number. What about this? Is this a constructible number? Yes. It is, right? It's a 4th root, but a 4th root is the square root of a square root. So that is constructible. Now we're really getting somewhere. So the cube root of 2. So we want to know, is this a constructible number? Can we write it using the arithmetic operations and square roots? Probably not. I mean, it looks like you probably couldn't. I don't know if that's a proof, though, but probably not. But you can see we're getting closer to being able to answer these questions about the impossibility of these problems. But if you get too confident about this and you're like, yeah, there's no way we could construct this, then here's a cautionary example. So this one looks just as bad as the previous one, right? But that number is actually just 1 plus the square root of 2. This is easy to verify. If you cube the left-hand side, you get 7 plus 5 root 2. If you cube the right-hand side, you can, if you're bored, you can do it on your paper. If you cube that, you're going to get 7 plus 5 root 2. So even though it doesn't look like it, that is a constructible number. So that makes us a little bit uneasy, but at least it looks like we're heading in the right direction. And finally, can we write pi using these arithmetic operations and square roots only? Again, probably not, but we definitely don't have a proof at this point. Okay, so Descartes pushed us a long ways towards solving these problems. So this is just a reminder of what our four numbers are here. So remember, we start off with a unit line segment, and we want to know, are these constructible numbers or are they not constructible numbers? If the cube root of 2 is constructible, then we can solve the problem of doubling the cube. If cosine theta over 3 is constructible for every theta, then we can trisect any angle. If cosine 360 over n is a constructible number for all n, then we can construct every regular polygon. And if pi is a constructible number, we can square the circle. Okay, so we're rephrasing our problems in what seems to be a much better way. Okay, so let's talk about regular polygons. So this is one of the mathematical greats, Gauss. And out of curiosity, how many of you are 19 years old or younger? A few of you, okay. So some of you still have some time. When Gauss was 19 years old, he proved that you could construct a regular 17-sided polygon. So he proved this when he was 19 years old. Notice I didn't say that he constructed it. What he did was he proved that you could construct it. So remember what that means. That means that cosine of 360 over 17 is a constructible number. Okay? And it turns out what that number is that number from the earlier slide. So I said it was famous, but then I said it wasn't famous, but actually it is a famous number. So cosine of 360 over 17 is this long thing. And when Gauss got to this point, he knew that the 17 gon is constructible. Okay? And this picture here actually is a postage stamp that I got on eBay. Here's Gauss's 17 gon. Here is a compass, and that's not really a straight edge, but I guess it has a straight edge here. So that's kind of cool. Gauss was extremely proud of this result, and he often said that this is what made him want to continue to pursue mathematics. He actually wanted the 17 gon on his tombstone. I don't think that actually happened, but years later they built a monument to Gauss in Brunswick, and if you look at the side by his foot here, if you zoom in, it does have a 17-pointed star, which is in honor of his 17 gon. So that's kind of neat. Okay, so here's what Gauss actually wrote. He says, "It seems that one has persuaded oneself ever since Euclid's time that the domain of elementary geometry could not be extended. At least I do not know of any successful attempts to enlarge its boundaries on this side. It seems to me, then, to be all the more remarkable that besides the usual polygons, there is a collection of others which are constructible geometrically. For example, the 17 gon. So actually, Gauss did more than just show that the 17 gon was constructible. He found other ones as well. So if we go back to our chart here, we can color the 17 gon green. It turns out if you read what Gauss did, this is probably not a surprise to anyone. It was very deep. It had to do with geometry, but it also had to do with complex numbers. And also, surprisingly, number theory fell into the conversation here. So again, I apologize that this is at the bottom of the screen. You can look at the TV monitors if you need to see it. We need to talk about something called a Fermat prime. So Pierre de Fermat was looking for a prime generating function, a function that would spit out prime numbers. And he observed that 2 to the 2 to the m plus 1 seemed to generate prime numbers. So for example, when m is 0, we get 2 to the 2 to the 0 plus 1, which is 3. 2 to the 2 to the first plus 1 is 5. 2 to the 2 squared plus 1 is 17. And then it continues 257 and 65,537. Those are all prime numbers. And so he believed that this would just continue generating prime numbers. And he was not able to prove it, but he left it out there as a conjecture. It turns out, unfortunately for Pierre de Fermat, that the very next Fermat number is composite. And does anyone know who factored that next number? Another one of the greats? Euler. So Euler was able to factor the next one. And it turns out that as far as we know, none of the rest that we know are actually prime. They all seem to be composite. But we do have these 5. And what Gauss discovered is that if n is a product of distinct Fermat primes, and then remember you can always double the number of sides of a polygon, but if it has that form, then the regular n-gon is constructible. Okay? So remember, we had 3 and we had 5, and we had 3 times 5, which is a product of them. 17 is another one. Like 15 times 17 would be another constructible one, etc. Note that it says distinct Fermat primes. So 9 is 3 times 3, but it's not the product of distinct Fermat primes. And 7 is not a Fermat prime at all, so that does not fall under Gauss's theorem. So you might think, all right, we're done with one of the 4 problems. But actually, we're not. This doesn't go the direction that you want it to go. This says that if the number has this form, then it's constructible. So it doesn't say that these are impossible. It just doesn't fit the hypotheses of the theorem. And so as you might imagine, Gauss did think about the converse of this theorem. And in typical Gauss fashion, he gave a really annoying comment about that. This is what he wrote. He said, "The limits of the present work exclude this demonstration that the others are not constructible, but we issue this warning lest anyone attempt to achieve geometric constructions for sections other than the ones suggested by our theory. For example, sections into 7, 11, 13, 19, etc. parts, and so spend his time uselessly." So in other words, Gauss is saying, the rest of them are not possible. Trust me, don't waste your time. But he didn't prove it, and as far as we know, he never wrote it down. It has not been discovered in his notes anywhere. So Gauss was saying that this is an if and only if theorem, and that these are impossible. The red ones are impossible. The green ones are possible. But he did not prove it. So it turns out Gauss was correct. That's also probably not a shocker. But we had to wait a little while to get a firm proof that this really is an if and only if theorem. Okay? And so it turns out that we can thank one person for knocking off 3 of these impossibility problems. And this is a mathematician who probably needs no introduction to you, because you probably all know him, right? Here's Pierre Wansel, right? He is one of the main heroes of our story, but he is not a very well-known mathematician. I did a screenshot of his Wikipedia page, which is longer than my non-existent Wikipedia page, but for someone who solved 3 of these 4 problems, that is an unbelievably small Wikipedia page. We don't even know what Pierre Wansel looked like. The mathematical writer Brian Hayes wrote this quote, and I love it. It says, Pierre Wansel is hardly a household name, even in mathematical households. It turned out Pierre Wansel died very young. He was not sort of part of the mathematical establishment. Here's what one of his contemporaries wrote after he passed away. He wrote, "Wansel was blameworthy for having been too rebellious to the counsels of prudence and of friendship. Ordinarily, he worked evenings, not lying down until late. Then he read and took only a few hours of troubled sleep, making alternately wrong use of coffee and opium, and taking his meals at irregular hours until he was married. He put unlimited trust in his constitution, very strong by nature, which he taunted at pleasure by all sorts of abuse. He brought sadness to those who mourn his premature death." So he is the hero of our story, and we don't know all that much about him. Okay, so let's just put things in context here. Descartes' geometry was 1637, so we're now 200 years after Descartes. Now algebra is really a mature field, and as you can see from this theorem, the algebraic language is very modern. So Pierre Wansel proved the following thing, that if A is a constructible number, then it is the root of an irreducible polynomial f with integer coefficients, and the degree of f is a power of 2. So in case some of these terms are unfamiliar to you, being the root of a polynomial means that you get 0 when you plug it into the polynomial. Irreducible means this has integer coefficients. You can't factor it into into 2 smaller polynomials with integer coefficients, so you can't factor it any further. The degree of a polynomial is the largest power of x, and power of 2 just means 2, 4, 8, 16, etc. Okay? So this was the theorem that we needed, and actually we need the logical contrapositive of this. So the contrapositive says that if A is the root of an irreducible polynomial with integer coefficients whose degree is not a power of 2, then A is not a constructible number. And so with this information, we can solve 3 of our 4 problems. So let's look at the cube root of 2. The cube root of 2 is a root of this polynomial, right? X cubed minus 2. If we plug it in here, we get 0. You can prove that this polynomial can't be factored any farther, so it's irreducible. And the important fact here is that this exponent is 3, and 3 is not a power of 2, and therefore it's impossible to double the cube, right? The cube root of 2 is not a constructible number. Okay? The angle trisection problem was the next one. So remember, we can trisect some angles. The question is, can you trisect every angle? So to understand this, we need this trig identity, which I don't know about you, but I never memorized this when I was in school. But if you plug in 20 degrees for theta here, then this is 60 degrees. And if you play around with this a little bit, you'll see that cosine of 20 is a root of this polynomial with integer coefficients. Okay? It turns out that this polynomial is irreducible. And again, it has an exponent of 3, a degree of 3. And therefore, cosine of 20 is not a constructible number, which means you cannot construct a 20-degree angle, which means you cannot trisect a 60-degree angle. And so that solves that problem, proves that it's impossible. The proof for the regular polygons is a little bit more involved, but it's still the same kind of idea. I'm not going to talk about that. But I do want to share with you what I think might be the greatest page in all of mathematics. So it turns out Wansell's article was pretty short, and it turns out that all 3 problems were proven to be impossible on the same page. So if you look here, this has the doubling of the cube up here near the top of the page. A little farther down, we see the angle trisection, right? And you can see here's our polynomial, for example, and here's our polynomial. And down at the bottom here is the division of the circle into the circumference into n parts. So this is the regular n-gon problem. So I think this is perhaps the greatest page in all of mathematics. You guys probably know that Newton and Einstein had their famous miraculous year. And so I think we should call this the miraculous page, this one page here. Okay? Okay, so finally, so that was 3 of the 4 problems. Wansell solved all 3 of these. The 4th one, the most famous one, was the trickiest of them all. And this one took longer to solve. And so you guys may know that Abraham Lincoln was a fan of Euclid's elements. He liked to work through these geometry problems and thought that this way of geometric thinking was good for a lawyer and a future president. And so I came across this amazing anecdote of his law partner Herndon walking in on Lincoln doing some geometry. And so this is when Lincoln was on the circuit court. And so this is what Herndon wrote. I will read it to you. He wrote, "Lincoln was sitting at the table, and spread out before him lay a quantity of blank paper, large heavy sheets, a compass, a rule, numerous pencils, several bottles of ink of various colors, and a profusion of stationery and writing appliances generally. He had evidently been struggling with a calculation of some magnitude, for scattered about were sheet after sheet of paper covered with an unusual array of figures. He was so deeply absorbed in his study that he scarcely looked up when I entered. I confess I wondered what he was doing. When he rose from his chair, he enlightened me by announcing that he was trying to solve the difficult problem of squaring the circle. For the better part of the succeeding 2 days, he continued to sit there engrossed in that difficult, if not undemonstrable proposition, and labored, as I thought, almost to the point of exhaustion." So at this point, the problem of squaring the circle was still an open problem. It had not been proven impossible. I think mathematicians knew that it was probably impossible, but it was not proven to be impossible when Lincoln was working on this. And so our final question is pi a constructible number? And so pi has a long and rich history, which I'd love to share with you. I believe that pi should be called Archimedes' number. He contributed to our understanding of circles and of pi in so many different ways. Brian mentioned that article I wrote about who first proved that the circumference over the diameter is a constant. The punchline is Archimedes. He also came up with these famous bounds for pi and so many other things related to the problem of squaring the circle. But Archimedes didn't solve that problem. A little later, not a little later, 2,000 years later, Johann Lambert proved that pi is an irrational number. This is an amazing theorem and quite an accomplishment, but this also isn't what we need to say that it's impossible to square the circle. And so finally, what we need, let's go back to Pierre Wansell's theorem. Remember, Pierre Wansell's theorem was all about when these numbers are roots of a polynomial. And it turns out that there are certain numbers that aren't roots of any polynomial with integer coefficient. These are called the transcendental numbers. And so if a number isn't the root of any polynomial with integer coefficients, then it is certainly not the root of a polynomial of degree 2 to the n. And so the final piece in the puzzle was proven by Ferdinand von Lindemann in 1882. He proved that pi is a transcendental number, and therefore it's impossible to square the circle. And so that was the ending point for these four very famous problems. So that is the end of the story. I promised you we'd have one further activity, and so we are probably running a little short on time, but I'll walk you through this, this problem, which you can carry out at your table. So you don't have to draw anything just yet. This device is called a tomahawk. We don't actually know who came up with this geometric shape. The earliest we can find is that it was referenced in 1835. And so you can use this tomahawk to trisect any angle. And so here is how it works. This is very specially designed device where if you line it up so that this corner of the tomahawk hits one line coming out of the angle, this edge passes through the vertex, and then this circular arc right here is tangent to this line segment. So if you line those three things up through this corner, the edge passing through the vertex, and this guy being tangent, then it turns out that this right here is 1/3 of the angle. And so this might seem mysterious. The math behind it is that if we take the head of this tomahawk and divide it into 3 equal line segments, and then the radius of this circular arc is the same as this segment right here, then hidden in here you have this right triangle, and this right triangle, and those are all congruent right triangles. And therefore, these 3 angles are all the same. So you have to specially design. Actually, someone pointed out to me, what's interesting is you can make the tomahawk with a compass and straight edge. So you can make a device with a compass and straight edge that can solve these problems, but you can't use a compass and straight edge to solve these problems. So as a final activity, let's walk through constructing the regular nonagon. So I'm going to walk you through this. You can follow along yourself if you like. If you want to just try it on your own, you can block your ears here if you want. So for this one, I want you to start with the rusty compass number 1. So this is the big circle, and you want to draw the big circle here and put a little mark where the center of the circle is. And our objective here is to construct a regular 9-sided polygon inside this circle. Okay? So the next step that I want you to do is pretend like we're constructing the hexagon. Okay? So you can take that same circle and put the center anywhere on the circumference. And so the circle is going to pass through the center of the original circle, and you just mark off where it crosses the circle on your original circle. So you can have this point which you can mark, this point which you can mark, and also mark the center. So that's going to be right there. So right now we're going to have 4 points, this point, this center, and this point on the circumference. Okay, so this was the way we started off constructing the regular hexagon. And we're going to do one more step that's like that. So if we draw a line segment through these 2 points, that's going to give us our point on the opposite side here. So we draw that, that gives us this point. So I don't want to get ahead of you guys. Okay, so right now we have these 4 points on the circumference, and if you notice, this point right here, this point right here, and this point right here, those are vertices of an equilateral triangle, which are going to be vertices of our eventual 9-sided polygon. And so we could trisect this angle using our tomahawk, You could, it turns out the geometry is going to be a little bit weird because of the size of your tomahawk. So it turns out what's going to be easier for us is to draw these two line segments here. So let's draw this one and this one. So draw these two, join these two, and join these two. Okay, it turns out it's going to be easier with your tomahawk to trisect this angle right here. So these were the vertices of our equilateral triangle. We join these two to get a line segment. We join these two to get a line segment. So far we've done nothing that Euclid could not do, okay? But it's the next step that is non-Euclidean. So now we want to use our tomahawk. So remember how this works? You want to line it up so that the corner is on this ray, the blade is tangent to this line segment, and the handle, the left-hand side of the handle, passes through this center. So when you get that, draw a line segment along here. Okay. It requires a little finagling to get this to work. Okay. So what this is going to do, it's going to trisect this angle right here. So we're still working on it. Okay, so that gives us this point right here. Okay, and I claim that this point and this point are adjacent vertices on the regular nonagon. So let's look at this angle right here. So this angle is 60 degrees, and so this angle right here is 2/3 of 60 degrees. So that's a 40-degree angle. So that's a 40-degree angle, but 360 divided by 9 is exactly 40. So this is 1/9 of the circle. And if I did everything right on my printout, this should be exactly the radius of the rusty compass number 2. So if you had an actual compass, what you'd want to do is sweep out this arc, and that would find your next one, and then sweep out the next arc and work your way around. But now you should be able to put the center of rusty compass number 2 here, and that's going to give you a point over here. And you can sort of march your way around, and that should give you all of the vertices of your regular nonagon using this compass. So if you did everything correctly, and if I did everything correctly making the worksheet, your rusty compass number 2 should be able to give you all these edges here. Okay? And so I think that is probably a good place to end. Thank you guys so much for coming out, and it was nice to speak to you.
All right, if anyone has any questions, you can raise your hand. I'll bring a mic.
Given that we can use the compass and straightedge to draw a marked straightedge and to draw a tomahawk in no different a manner to which we draw any ordinary geometric construction by just making a mark just outside the paper. How is that cheating or going beyond the rules in some way, given that we're using the same tools to make the extra construction?
That's a good question. I mean, I think it's sort of a meta thing. So can you use these tools to make new tools to solve some of these problems? And you can do that. Like you said, you could do you could create the marked straight edge, and you could construct the tomahawk and so forth. I mean, I think the way these problems are structured is you have a well-defined set of rules, and making new tools is not one of the options that Euclid gave you. So I think it's a neat fact that you can use the compass and straight edge to make tools that allow you to solve new things, but that doesn't mean that you can solve them with just the compass and straight edge. So it's all about what the rules are, and so that would be breaking the rules, so to speak. That's a great question.
So given that the algebra here was able to solve a geometric problem, is it now possible at all to trace backwards from the algebra and create a geometric proof?
Not that I know of. I mean, it's pretty elaborate. I mean, the amount of algebra that needs to be built up is so sophisticated, it would be hard to work your way backwards. And I would say, historically, this is what geometers would have that's exactly the complaint that generations of geometers would have, is that the algebra hides all this geometry. So it's true that you could use algebra to solve these geometry problems, but it's sort of impossible to follow the geometry behind the algebra. And so that's what all these issues were with people who were refusing to accept algebra into mathematics. I also want to mention that this clash that I read about between algebra and geometry reminded me a lot of when I was younger, let's say in the 80s and in the 90s, when computers and calculators were starting to enter the scene and being able to solve mathematical problems. And the older generation did not like that. They thought this is not the way we do mathematics. But the younger generation said, this is how we do mathematics. This is fine. And so the older generation is retiring, and the younger generation is coming along. And so I think these kinds of complaints are that is a very historical complaint, and that's that we can't follow the geometry while we do all this algebra. Yeah, thanks.
So let's give the speaker another hand.